And I know what you all want. You all want even more pi. The people demand it. I will provide it. Okay. But first, I want to talk a little bit about just what pi is, so we're all on the same page. And in fact, I'm even going to insult your intelligence by starting with the definition of a circle. And I know we all know this, but it's going to be important later, so let's make sure we're all on the same page. So, okay, we start with a point, let's call it the center of our circle, and we have a distance away from the center, call it the radius. Then the circle with that radius is the set of points that are exactly that distance away from the center. Okay, nothing mind-blowing here. Then pi, the way we define pi is we say, okay, take the distance around that circle, that's the circumference, and then take the distance from one end of the circle to the other through the center. That's the diameter. And pi is whatever number you get when you divide the circumference by the diameter. Okay, so now, Miss Sangster, I'm gonna quiz you on this later. Okay, so next, we know historically, I think the oldest measurement of pi that we have is, 4,000 years old. And in this document, it says that they measured pi to be about 3 1/8. They probably measured this physically by like drawing an actual circle. And if you say, drew a circle, you had a string and you made that string the length of diameter, and you just asked yourself, how many times can I wrap that string around the circle? Well, you'd say it's a little more than 3, a little more than, or less than 3 1/2, less than 3 1/4, or I don't know, maybe a 3 1/8. So these are kind of our oldest measurements. So pi has been an important constant for a long time. But our first theoretical calculation is due to Archimedes, a little more than 2,000 years ago. And he was able to say kind of rigorously that, actually pi we know is going to be between 3 and 10^71 and 3 and a seventh, or, converting to decimals, 3.141 and 3.143, which we know is actually already very accurate. The symbol pi was first used in 1706 by somebody who did nothing else famous, but did happen to use pi first. Okay. Now, when I just told you how we calculate pi, I didn't say anything about how big our circle is. So does it actually matter what size circle we use? You're probably saying in the chat, no, but like, what if you drew a really big circle? Now, I mean like a really big circle. Like say you drew a circle that was 1,000 miles in diameter. Does it matter? Does pi now matter? I claim that it does. Guys, we live on a sphere. It starts to matter. Okay, so let's go back to our definition of a circle and talk about how do you draw a circle on a sphere? Well, I claim you want to just do as normal, like I said on that first slide. You take a point on the sphere. Here, I've chosen the North Pole just for ease of like visualizing what's happening. And then you say, take a distance away from that point. And then you say, okay, well, a circle on the sphere is going to be the set of points that are exactly that distance away. So, okay, this is what your circle looks like on this sphere. And now the question is, all right, well, what approximation of pi do you get on a sphere? Well, okay, it depends now on the size of the circle you draw. And so let me ask you, what value of pi do you get if you draw the biggest circle possible? So in this case, if our point was the North Pole, if that was our center, then the biggest circle you could draw is at the equator. And so you have your, all right, we've got some answers in the chat. Okay, if our circumference is the equator, which is all the way around, and our diameter is now going halfway around, then this means if we took our diameter and we tried to wrap it around, we would be able to wrap it around twice. Yes, Mr. Marshall, second time's the charm. So yes, we would get a value of pi that is 2. Okay, but is that the smallest value of pi we can get? Can we get a smaller value of pi, or is that our limiting case? So in the chat, what do we think? Can we get a smaller value of pi? No? Yes. I see both yes and no. I claim that you can get as small a value of pi as you want. Because, all right, no need to stop at the equator. Just keep going farther down and draw circles closer and closer to the South Pole. And as you do that, your circles are going to get smaller and smaller, so your circumferences are going to get smaller and smaller, but the diameters are going to get larger and larger. So in that fraction, your numerator is going to get small, your denominator is going to get big. That ratio is actually going to get as small as you want. All right, so then the next question to ask is, well, how big a circle do we have to draw to get a value of pi equal to 3? And it turns out you have to draw some circle of about 2,000 miles in radius. And that is my proof that pi actually is sometimes equal to 3. Okay. But I know what you're thinking. You're saying, Dr. Hagen, you're cheating. That's cheating. Why are you restricting us to staying on the surface of the Earth? Just draw the circle in space. And to that, I say, you beautiful, sweet, innocent souls, that will not save you. Space-time is curved. In fact, okay, yeah, draw your stupid little circle in space. Draw one around the Earth. Okay, you draw a circumference, you draw a circle around the Earth. I'm sorry, Ms. Zahn, I got a little excited. Draw your circle around the Earth. If you say, took that circumference of the Earth around the equator, say, measure the equator, divide by pi, your measurement for the true diameter of the Earth would actually be off by about 4.5 millimeters. Okay, so the fact that space-time is curved means that if you try to, say, draw your circles in space, you will run into the same problems. In fact, you might run into worse problems. Because suppose you tried to, say, draw a circle around our galaxy, and there's a black hole at the center. And now, because space-time gets so warped around a black hole, I don't even really know what's going on as you try to cross an event horizon, does pi even make sense if you are trying to draw a circle around a black hole? I ask you to direct all follow-up questions to Mr. Pruduicki. This is his problem as a physicist, not mine as a math teacher. Okay, but all right, enough of this. You all wanted more pi, not less. Can we do this? Can we do this? Can you imagine a surface where you can actually get a bigger value of pi, or is this curvature always going to give us a smaller value? So I don't know. In the chat, what do you think? Is it possible to get a bigger value of pi? All right, I see some yeses. We've got some, hopeful people here. We've got some optimists. Yes, we can. One way to do it is to say, okay, just have a very wavy surface. In this case, your diameter, I guess you could think of the surface, and then you could think of a flat surface also kind of going through that same center. Then the the diameter between would be the same for this wavy surface and plane going through that same part. But now the circumference of the circle on the wavy surface is going to be much larger than the circle you would get on a flat plane. And so your denominator is going to get bigger. And so the wavier you get, the bigger your denominator will be. And so you could get a value of pi as large as you want. This also works with a Pringle, which, of course, Pringles are going to come up multiple times today. But yes, a Pringle is also a surface where if you drew a circle centered at the saddle point, you would get a larger value of pi. Okay, and I am almost out of time. So this part, just for funsies. This is an exercise for anybody who wants to explore these ideas further. All right, so there's something called taxicab geometry. And in this geometry, you could think of all of the points are on a fixed grid. And the only way you can get from one point to another is by walking along grid lines. And so let's say this is our point of interest. Then we could say, well, how far away is this point here? And we're not talking about, you can't just travel along the diagonal. You are stuck on the grid lines. And so we would say, that I saw in the chat, somebody put 4, and I agree, because you would go 1, 2, 3, 4. You could get there a different way, maybe to go 1, 2, 3, 4. But the smallest number of steps you would need to take to get to here and here is 4, which means actually this point, whoops, lost me. This point here is farther away than this point, because this point is only 1, 2, 3 away, and this one is 4 away. So even though, like, on, you know, if you were to draw a straight line, this would be closer, but in taxi cab geometry, this one is closer. And now the question is, what does a circle look like? Say a circle of radius 3. What does a circle of radius 3 look like if we were doing taxi cab geometry? All right, Kate, I know some of you know, and I'm excited for you, but I'm going to leave this as a let people kind of think more about this. So yeah, okay, what does a circle look like? Now the question, once you know what a circle looks like, ask yourself, what value of pi do you get? And then the question is, what does this value of pi change depending on how big you draw your circle? Okay, so this is just something for fun to think about. I'm not going to reveal any of this. I mean, I guess I can reveal what shape you get. So if you don't want to know what shape you get, close your eyes when I count down. Otherwise, I'll show you what shape you get in 3, 2, 1. That is the circle in taxi cab geometry. Okay, you can open up your eyes. Happy Pi Day, everybody.